All right. Hello, everyone. Welcome to Beginner Track Session 4. Today, we're going to talk about bit masking. It's not a very common topic you would encounter unless you take CS32. Have you guys taken CS33 yet? Taking it right now? You're also taking? Oh, okay. Great. You guys would be experts in this area. All right. So, first off, here's the agenda of today. We're going to talk about like bits, binary stuff, and then converting from decimal to binary, converting from binary to decimal. I'm going to talk about bitwise operators and then how we can use them to our advantage in competitive programming. Now, first up, there's this very famous joke about binary. There are 1-0 types of people in the world: those who understand binary and those who don't. Yeah. Okay. Since you guys both know binary pretty well at this point, I'm just gonna fly through these slides real quick so that you can get to the practice problems and the interesting part. And first up, like you know that when you write 1, 2, 3 in decimal, it means you have 100, 2 tens, and then 3 ones. So if you write it out, it's like 1 times 10 to the square, 10 squared plus 2 times 10 plus 3 times 10 to 0. And we can apply the same logic to base 2, right? In this case, 101 is 1 times 2 squared plus 0 times 2 plus 1 times 2 to the power 0. And that gives us 5. It gives us 5. So how do you convert from decimal to binary? You guys want to help out? Contribute ideas? Well, what do you do when you are required to convert a number to binary? Wait, are you asked to do that in CS33? No. Not too often. Okay, how would you do that? Okay. Okay. That's one way of doing it. But today I'm going to talk about another. And in my opinion, this with like implementing this algorithm this way, at least it's easier for me to implement. Okay, so let's look at number 13, right? If you notice that binary numbers, like the last digit of the binary number tells you the parity of this number, whether or not it's odd or even, right? 13 is an odd number, so we know that the last digit of 13. That's also we know that the last digit of binary representation would be 1. Thus we know, okay, we have the last bit or like the least significant bit of 13. How do we find the other bits? Notice that ideally we want to shift the entire thing to the right by one bit, and then we apply the same logic again, right? If it's even, then this bit would be 0. If it's odd, this bit would be 1. So how do we do that? What we can do is dividing the number by 2. So 13 divided by 2 is 6. We ignore the remainder. We apply. This is integer division, so we ignore the remainder, and then we get 6. Essentially, we're just truncating the last bit when we divide the integer by 2. Now we know that 6 is an even number, so the second least significant bit is 0. So on and so forth. We continue our process, and finally we get Finally we get 0, and then we know that 0. Well, no matter how you divide 0 by 2, you're still gonna get 0. So there's no more number left in this 13. We've already taken out all the information in it. So yeah, we know that the final binary representation of 13 is just 1101, and we can stop our algorithm here. And yeah, here's a quick quiz on to see if you know how to convert numbers from binary to base 10 and vice versa. You guys can take 10 seconds to go over them. They're pretty simple. All right. So here's the answers. And yeah, here is the code, the implementation of the algorithm I just described. So as you can see, first we are given an integer and we want to convert it into a string. And in order to do this, we need some sort of like, we need a variable to store it. So we first declare s equals the empty string. And if the number we want to convert to binary is 0, we just return 0, right? Otherwise, we determine whether or not n is even. If n is even, then we concatenate it 0 to the string, like to the front of the string. If n is odd, then we add a 1 to the front of the string, and then we divide n by 2. And finally, after this process is done, we just return s, and then it will give us the binary string for any integer, any positive integer. Okay, here's the link to this week's example problem. See if you can click on it and open up the contest. We are going to, so first we're going to take a look at this example problem. And you guys, I'll give you guys 5 minutes to work on it, and I will go over the solution after that. Since you guys are both really experienced already, see if you can finish the implementation in 5 minutes. And I'm gonna go over the solution to this problem. So one observation you need to make to solve this problem is that no matter how many zeros you insert in between two ones, it will not change the position of your finger that's like responsible for one, right? So what you can do is, after turning all these characters into their ASCII code, and then turning ASCII code, the ASCII number into binary, you can isolate the ones and zeros and then treat them separately because they do not affect each other. What I mean, wait, 1 second. Okay. Oh, right. Here's the solution code starter. So taking the input for this problem is a little difficult and annoying. So if you are stuck on taking the input, you can refer to this. And yeah, here's an ASCII table, right? It's basically a mapping from characters to numbers, and then with the numbers you can convert them into binaries. So what did I mean when I say that like adding an infinite, like however many zeros between ones does not affect the position of your finger that types ones? Well, think about this. Like, take a look at this example. 1 0 0 1 0 1 0, right? So the first number is the first bit is a 1, which means to type this you would well, let's say the left key, use your index finger for the left key, and you use your middle finger for the right key. You would have to press the left key with your index finger, and then you see 2 zeros. So you press the right key with your middle finger once, and then you raise it up to type the second 0. And then now you encounter 1. You raise your index finger, and then you see a 0. So you press down your middle finger, and then you see a 1. You press down your index finger. So notice that like the zeros and ones are completely independent, right? And only when we press a key an even number of times, our finger will be free. So for example, in this case, there are a total of 4 zeros and 3 ones, which means after typing this character or like this binary string, your index finger would still be on the key, and then your middle finger would be free. And what if after typing this character, you want to type this 1 0 0 0 0 1 1? Now, notice that in addition to the 4 zeros and 3 ones we had before, like in the first character, we have 4 more zeros and 3 more ones. So after typing these two characters, our index finger would be free, and our middle finger would also be free, right? The idea is basically in this simple example. And what you want to do is you want to convert the string, like each character of the string, into its ASCII number. And then for each ASCII, you convert it into a binary string. And then you basically just count the number of ones and the number of zeros, the total number of ones and total number of zeros in this binary string, and then see if both of them is even. If both of them are even, then your fingers are free and you can go to the washroom however you like. You can go to the restroom however you like. If either one of them is odd, then unfortunately you're stuck. So yeah, we can basically convert everything into like a super long binary string, and then we count the number of zeros and the number of ones in the end. Now, moving on, I'm going to talk about bitwise operations. Just like their Boolean counterparts, bitwise operators also has like an AND operation. What this does, like its name suggests, is that you apply a Boolean AND on each corresponding digit of two integers. For example, if you do x ampersand y, it means you want to AND the two least significant digits, like, and then the second digit and the second digit and the third digit, I know that like this sounds a little bit confusing, but we can take a look at an example. If x is 13 and y is 11, we can first like write out the binary representation of these two numbers. 13 is 1101, 11 is 1011. Notice that the bit position is numbered from right to left. This is just convention. But the most significant bit is still on the left. Now, if we apply a bitwise AND on these two numbers, notice that the first bit, or like starting from the left, bit position number 4, both of these two bits are 1, which means the result will be 1. And then for position 3, 1, 0, that would give us 0. 0, 1, that would give us 0, and then 1, 1 would give us a 1. So the final output of this would be 9. 1, 0, 0, 1, which is 9. Similarly, we have bitwise OR, which applies OR to each digit separately. And with the same two numbers, let's take a look at what the output would be. So bit position 4, that's a 1. 3, 1 and 0, that gives us 1 or 0, that gives us a 1. And then bit position number 2, 0 or 1 is also a 1. And finally, 1 or 1 is also a 1. So the result would be 1, 1, 1, 1, which is 15. Okay, here's some like short examples that you can try out by yourself. I suggest you take a look at number 3 and think about how you would approach it. And if you figure out how to solve number 3, think about how you could apply this in your code. Sometimes, what could be an application of this? You guys want to move on? Want me to move on? Good. Okay. So here's the result. Here's the answers. So for number 3, you don't want to convert. You definitely don't want to convert that number into a binary, right? Into a binary string by hand. What you can notice is that 1 only has 1 digit. That's 1. So if you AND a number with 1, like bitwise AND a number with 1, you are effectively only taking the last bit of that larger number. This is also another way of testing the parity of the larger number. Okay, left shift operator, written as like 2 smaller than sign, shifts the left operand by y slots. So for example, if you have, let's say, 2 left shifted by 2, it means you want to shift the bit pattern of 2 to the left by 2 bits. Effectively, it's the same as multiplying the number by 2 to the power of y. All right, let's take a look at another example with number 13. If we shift, well, here's the bit pattern of 13, and if we shift the pattern to the left by 2 bits, we would get like 110100, which is 52. And similarly, there's also the right shift. It shifts the number to the right by 1 bit. And with x equals 13, y equals 2, we have like the final result would be just 1, 1, which is 3. Notice that we truncated the last 2 bits, and that's just how redshift works. And then here's some examples that you can try out if you're interested. Yeah. Now, since you guys are probably like very familiar with this, I'm just gonna skip over this part. Oh yeah, another thing is that order of operation matters in bitwise operations, and it's actually quite complex. If you look at the Wikipedia page, the order is it's not very easy to remember the order. So in case you need to like chain a bunch of bitwise operations together, just use parentheses. They save less. All right. Here's just an example of where you could use bitwise operations instead of normal divisions and mod. Like as I said, instead of doing n mod 2, you can do n bitwise and 1 to determine whether a number is odd or even. Similarly, instead of doing n divided by 2, you can do n right shifted by 1. That gives you the same thing. Okay, so enough of these like operations. Why do we care about fits, right? I'm sure you guys also wonder, why do we want to do this data lab thing in CS33? Here's the thing. Bits are like very fundamental in computer science, and then sometimes you can do like really cool stuff with them, and you can only realize these applications of them by practicing using them. For example, in this, like suppose we look at a graph of nodes, right? And then I want to do DFS over the graph. How can I keep track of the nodes that I have already visited? From the past couple of weeks, we learned that we would use the visited array. In fact, essentially, for each node, we would have a slot storing a Boolean value, telling us whether or not we've already visited this node. Initially, when we haven't started DFS, every slot would be false, and every slot in the array would be false. Now, if we start DFS at like on node 6, right, we would mark slot 6 of the array as true. If we move to node 4, we would mark node 4 as visited. After moving to node 3, we would mark node 3 as visited. And notice that if I, instead of writing true or false, I write 1 or 0. This looks oddly familiar, right? It's a binary string. And instead of using an array to keep track of it, we can use, well, an integer. And it greatly saves the memory we use because each bit only costs 1 bit. Each bit in an integer only costs 1 bit, whereas a Boolean variable costs a byte, if I recall correctly. So instead of having an array of Booleans, we can just use multiple integers in case we need to, we really need that extra memory space. Now, there are some other usage of bitwise operators. For example, we could use binaries to iterate through all possible subsets of a set. We could use binaries to determine whether 2 subsets are disjoint. And well, here's an example, right? If we have A, B, C, D, E, F as our set of objects, this could be like a set of ingredients when we are making pizza. It could be a set of homework that we need to do. There's a set of tasks we need to do for our assignment, right? And then we can just take out subsets of it. For example, ACE is a subset, BDF is a subset, and then using bitwise operations, we can determine whether or not like these sets have like any intersection. And yeah. Oh, okay. Here's the definition of a subset. In math, we say that a set is a subset of a set A is a subset of B if every element of A is in B. And in this example, what B is 1, 2, 3, 4, 5, 6. A is 1, 3, 4. And as you see, all the numbers are in B. All the numbers in A are already in B. So A is a subset of B. Whereas if A has a 0 in it, 0 is not in B. So 0, 3, 6 is not a subset of 1, 2, 3, 4, 5, 6. And then similarly, this is another usage of binaries. We can use binaries to determine set disjointness. We say 2 sets are disjoint when they don't share any element. For example, if we have the set A, B, C, D, E, F, and then we take out the subset ACE, we take out the subset BDF, how do we determine whether or not the two sets have any intersection? What we can do is converting the subset ACE into a binary string, right? Notice that in this table, ACE, in the row of ACE, for each element that's in the subset, we mark a 1. For each element that's not in the subset, we mark it as 0. Similarly, in the second row, for every element that's in the subset, we mark it as 1, and every element that's not in the subset, we mark it as 0. And then we can use the set operator, the bitwise AND operator, to determine which element, well, if there's any intersection between the two sets, and if there's an intersection, which element is like in the intersection, right? This is very fast, rather than running like a double for loop to determine whether a specific set element is in both sets. We can just do like a simple bitwise AND, and then we get the result we want. So the fundamental ideas behind these operations is that, like what we did over there with subsets, is that each subset corresponds to one unique binary string, right? If a particular element is in the subset, we have a 1 bit. If a particular element is not in the subset, then it's a 0 bit. And each binary string, also vice versa, each binary string corresponds to a unique subset. In math, we call this a bijection. And conveniently, each binary string can also be stored as an int. So using these properties, we can iterate through all subsets. We can come up with an algorithm that helps us to iterate through all subsets of a set. For example, here we have an array of 10 integers, 1 through 10. And then I've provided the first for loop for you. See if you can figure out how to iterate through all possible subsets of this array, and then print out each subset in a separate line. I'll give you 3 minutes to think about it and try to write out a solution. Okay. I'm going to talk about how you would do this in code. Let's take a look at the outer for loop first. We iterate through all the numbers from 0 to 2 to the power of n minus 1. This is the number of subsets in a set, right? And then for each number, for each integer, remember that there's a bijection between each integer and a subset. So we can just convert this integer to a binary string and then use this binary string to help us find the subset of this set. So first, we use the function we wrote earlier to binary to convert the integer number I to a binary string. And then we go through the binary string to find all the positions where there's a 1 in the binary string, right? If it's a 1, then we know that we want this element in the subset. So we print it out. If it's a 0, we skip it. And finally, after printing each subset, right, I want to enter a new line. So that's what the CL and line is. Okay, so I think we're ready to move on to the second example of today, Geppetto. This problem is more interesting than the problems we've gone through early, like in this workshop. And I hope you enjoy it. Take a look at the problem and see if you can solve it in a bit. And I'll talk about the solution to this problem after you guys have read through the problem and give it a try. hopefully you had enough time to think about this problem. It's pretty interesting, right? I like this problem a lot. So to approach this problem, let's think about the things we need to do. First of all, we need to encode the improper pairings, invalid pairings somehow. Like you don't want to put stracci on cheese. That's not good. And then after encoding the improper pairings and then like storing them in your program, you want to iterate through all possible subsets of ingredients and then check whether each subset contains any improper pairing. Now let's start with the first task. We want to encode the improper pairings. Let's say 1 and 2 is an invalid pairing of ingredients. And then you know that there are a total of 3 ingredients. How would you encode this? Well, you can just do something similar to the visitor array when we were doing graphs, right? Mark a 1 in the slot corresponds to 1. Mark a 1 in the slot corresponds to 2. And then mark a 0 in the slot that corresponds to 3. So basically, this gives us a binary string that tells us, okay, so if this bit is a 1, this gives us a binary string that contains only 2 1-bit. And then these 2 1-bit tells us exactly which 2 ingredients are invalid. So you shouldn't put them together. And then let's take a look at 2 and 3. So essentially just mark 2 as like the second bit as the 1 and the third bit as the 1. Okay, now that we have a way of encoding these improper pairings, we just need to go through every subset and determine if it contains a bad pairing. Now, let's take a look at all the subsets. In this case, there's only 3 ingredients, just so that we can fit the entire example on the slide. Right, starting with 0, 0, 0, we see that there's it does not contain any of the 2 bad pairings. So we move on to the next one. We see that 0, 0, 1 does not contain any bad pairings. 0, 1, 0 doesn't contain any bad pairings. 0, 1, 1, 0, 1, 1, in fact, is invalid. So we don't count that one. 1, 0, 0 is valid. 1, 0, 1 is valid. 1, 1, 0 is not valid. And 1, 1, 1 is not valid. Okay, once we have this figured out, we are basically done with the problem. And then notice that we've already talked about how to encode subsets as binary strings earlier in the presentation. We also talked about how to iterate through every subset and determine if it contains, how to iterate through every subset of a set earlier in the presentation. And the only thing left for us to do is to determine how, to decide how to determine whether a pairing exists in a subset. And then remember that earlier we also talked about how to find the intersection of 2 sets, of 2 subsets using binary string. And yeah, I'll leave that as an exercise. See if you can figure out, see if you can solve this problem. And then here's the starter code. You can use it if you want. Oh, actually, yeah, here's the starter code. You can use it if you want. And that's it for today's workshop. Here's the link. Please give us some feedback so we can improve in the future. And we really appreciate them. We hope we read every single feedback you guys give us. And then there's the link to the contest. I found actually, I didn't find them. Someone else found some interesting problems that also use bits and binaries. So you can take a look at them, see if you want, see if you can solve them. And yeah, thanks for coming. If you want to do the contest problem, definitely stay. We can help you with the problem if you happen to be stuck on anyone.